Mm-hmm.
All right, we're live. I'm gonna share this.
Hello.
Share this bad boy. We're live, but we're not gonna start yet. The streaming is what I mean. I'm independent right now.
So we're live, but we're not recording yet, right?
No, we are recording.
Oh, okay. Cool.
So people can tune in and see that the stream is active, but it's giving them a buffer time to actually tune in when the content starts. So I tweeted that the content's gonna start in 20 minutes.
Excellent.
Right. All right. Well, now we can actually talk about things.
Cool.
Okay. So what's your story? I kind of jumped into this, so all I know about you is that you're a researcher.
Sorry, it's hard to hear you.
Oh, let me turn this up a little bit. Is that better?
Yeah, that's great. Yeah.
So I was asking, like, what's your story before we start the meetup?
Sure.
Where are you? What
So
about you?
about myself or about where? Well, let's talk about, I guess, myself a little bit. When I was in college, whatchamacallit. So for my masters, I actually did research with my research scientist on cache oblivious algorithms and data structures. And basically, a long story short, that was sort of the start.
You're breaking up. Let me see if it's the signal or something. One
Hmm.
second. Okay, try now. Sorry about that.
All right, sure. Can you hear me?
Yep, great.
Cool. Yeah. So, well, I guess what I've been up to the last 7 years is, or the last 6.5 years is, I've been working at Tokutek, where we've been commercializing research done from Rutgers, Stony Brook, and MIT that basically building a right optimized database from the ground up. And what I mean by that is, like, a lot of databases historically, there have been a lot of innovations in the data structures being used within databases. I'm sure you might have heard of LSM trees and B trees. What we use are fractal trees. But what we've been spending our time doing is really, focusing on storage at the core and then building a database on top of it that is taking storage in mind, sort of, if that makes sense. So for our product TokuMX, which is a fork of MongoDB, we've basically taken MongoDB, we've completely ripped all of its storage out, and we've integrated our storage tightly into it. But in doing so, we've also modified a bunch of the existing algorithms to better take advantage of our storage and the characteristics of our storage, including replication and sharding. So that's essentially what we do.
Could you repeat that last bit? Because you were breaking up.
Sure. So the last bit was, I mean, we've ripped out all of MongoDB storage and we've replaced it with our own storage. And in doing so, we've also modified some of the existing algorithms they use in MongoDB to take better advantage of a right optimized database. namely sharding and replication. Like we've done things to make sharding replication a lot more efficient, to improve read scaling. We've done things to make sharding a lot smoother, to make migrations a lot smoother and have a lot less overhead, etc.
Okay, so you were dealing with a lot with like the way the storage engine basically, and making improvements on the storage engines and swapping out their own storage engine.
Well, let's actually. So, what you just mentioned, swapping out their storage for our storage engine, is really half the story. The other half of the story is also modifying existing algorithms within MongoDB. Like one example is, the transactional semantics, which I'm going to be talking about tonight, and also modifying things within replication and within sharding to take better advantage of our storage. Hello, I'm here.
All right. So the last I heard was that not just using storage engines. Sorry, can you hear me now?
Yes, I can.
Let me double check that I'm using the right microphone.
Mm-hmm.
All right. So
Mm-hmm.
let me click on
Yeah,
your little
I just thought we
avatar.
had a little lag there when I saw no response.
Yeah, I don't know. The connection's kind of shaky today. It's not
Mm-hmm.
cooperating the way I want it to. Anyway, okay, so it's not just about the storage engine, it's also about the algorithms that it uses for replication. Is that right?
It's the algorithms and it's the design of replication, really the whole database stack, replication, sharding, transactions, basically the end-to-end database stack, so to speak, that has been modified to better fit the characteristics of our storage. So, like, sort of one of the things I'm going to be talking about tonight is, MongoDB has only single document transactions, and their concurrency and their designs are currently designed centered around those characteristics. We are a transactional storage engine with MVCC, so we've modified some of the semantics to better take advantage of that to improve concurrency and therefore improve performance. Sharding is another story there. We've modified the sharding algorithms to make migrations a lot smoother. So hopefully, heavily reducing the need for separate migration windows to migrate data and to balance out your chunks. Replication, we've done things to drastically reduce I/O on secondaries to hopefully improve the read scaling you can achieve on replication. And these are all things that can't just be done by taking out one storage engine and plugging in another storage engine. It really requires a design end-to-end of the components that sit on top of storage that take into account what the characteristics of your engine are. And did I lose you again? This is not good. Hello?
Hey, hey! It looks like
Hey.
it's our connection here.
Should I try disconnecting and reconnecting?
No, I think it's more us rather than you,
Okay.
because I got a message about our network connection,
Okay.
and you were just sitting in the Hangout normally, right?
Yeah. I mean, since there are only two of us, it's hard to know, who's the one that's getting disconnected.
Yeah, we were getting a message of check your network connection, so I think it's us.
Okay. I turned my bandwidth down a little bit.
What's that?
I turned the bandwidth down for my video a little bit. Hopefully, you won't need the super.
Sorry, I didn't make that.
I turned my video quality down a little bit to hopefully limit how much.
Oh, okay. Maybe it might be that. Let's see how if I can manage to do it. All right. Let me get some confirmation from Bill.
Mhm. You could also ask him if it's me or if I. I just want to make sure I'm not the one that's getting disconnected from the Hangout.
Yeah, no, I think it's definitely us that's getting disconnected from the Hangout. But turning down the quality, I think helps the audio. So I think we can wait 5, 10 minutes more, and
Okay.
we can get started.
All right.
Just give Bill a call. We'll be right back. And we're back.
Mm-hmm.
I hope that we don't cut you off while you're giving your talk.
So if you guys get disconnected and I'm still speaking, the recording's still going, right?
You know, I'm not sure because, well, I guess it is because I guess it gets the data from the Hangout itself.
Yeah.
Yeah. Okay, that's good. That's good. So we're just like a Hangout. We're just like a Hangout spectator, even though I'm the admin. I don't think it matters.
Mm-hmm.
Okay, that's good.
So please let me know when I should start sharing my screen.
Yeah, no problem. I'm gonna give it like 4 more minutes, and we'll get started. I'll just give a short intro, and you take it from there.
Mm-hmm.
I'm on main room 5G. What? It's fast. I think it's more like a consistency problem than a speed problem. Maybe it's my computer. Shouldn't be my computer. It's a new computer. Yeah, it's a MacBook Air. Come on, man.
Mm-hmm.
Yeah. No, it's not the same. I prefer a MacBook Pro too. It's just it's way more expensive. That's why I went with an Air. Yeah. Yeah, the Air is a pretty affordable. Although it's right now since they made the MacBook Pro smaller, it's more an issue. It's more a difference of weight than it is of size. Like in terms of size, it's really not that much bigger. You know what? I'm gonna switch my Wi-Fi over just in case because
Mm-hmm.
it's actually opening pages and stuff is actually pretty slow for me right now. So let's try that. I'll be right back. I've had some issues with 4 gigahertz Wi-Fi's in the past.
Mm. Hello, you still there? Oh, there we go.
Okay, let's try this now.
Mm-hmm. There we go.
Yeah, sometimes 5 gigahertz acts really wonky.
Hmm.
Anyway, all right, let's get the show on the road.
All right.
Okay, so welcome everybody to the MongoDB meetup. So let me put myself on. Do this. All right, here we go. So, hey, welcome everybody to the meetup. Today we have a special guest, Zardosht Kasheff. Did I say that right?
Yes, you did.
Okay. All right. And so he's going to be talking to us about transactions in MongoDB, and he's down here from all the way from New York. And so please let me switch you on the main screen and take it away.
All right. Thank you very much. So I guess just first to check, I assume everybody can see the title slide. My name is Zardosht Kasheff, and I'm going to be speaking about transactions in MongoDB and TokuMX. And as I said, just I guess before we start, if there are any questions, I like questions, so definitely please feel free to go ahead and shoot questions at me. All right, so let's begin. So the agenda that I would like to set for tonight's talk is, at first I want to review the existing transactional semantics of MongoDB. I want us to understand how these semantics impact application development, and then we want to learn how the transactional semantics of what the transactional semantics of TokuMX are and its benefit. And down the line, when we get to TokuMX, I'm going to explain what TokuMX is and how does it compare and contrast to MongoDB. But first, let's begin with let's focus on MongoDB and let's understand what its transactional semantics are. So, what is a transaction? Well, according to Wikipedia, a transaction, quote unquote, comprises a unit of work performed against a database and treated in a coherent and reliable way independent of other transactions. Or a layman's terms for understanding this is basically a bunch of work that happens together. So a transaction must have the properties that you may be familiar with called ACID properties. And ACID is an acronym where each letter stands for something. The A for atomic, meaning either the transaction all fails or it all succeeds. C has to be consistent, meaning the database is always going from one valid state to another. It's always transitioning from a valid state to another. Isolated, meaning that the transactions are resulting in a state as though they're executing serially. So even if you got multiple transactions happening at the same time, if you sort of take a step back, you can look at the lay of the land and you could actually see what the order of the transactions that execution would be. And lastly, durable, where once a transaction commits, even if something bad happens, like a power loss or a crash, the transaction is going to survive.
So, do you think you could give us an example of the consistent part?
Sure. So there is a question of whether I can give an example of the consistent part, and I'm actually going to do you one better. I'm going to give you an example of I'm going to kill the following two birds with one stone. I'm going to give an example of a transaction that actually steps through each of these four properties, and I'm also going to present the transactional semantics of MongoDB. And I'm going to do this by using MongoDB's transactional semantics as an example. So let's actually get into an example of what MongoDB does and how MongoDB honors these properties. So first off, as you're probably familiar, MongoDB is a document-oriented NoSQL database that, among many things, supports secondary indexes, replication to an oplog, where replication meaning data can be copied to several other machines, and it also maintains a journal of write operations to replay in case of a crash. Now, for those of you that are familiar with relational databases, documents, when we say a document-oriented NoSQL database, you can think of documents as being analogous to rows, and the term collections as being analogous to tables. So conceptually, the same idea as rows and tables, but in MongoDB they're referred to as documents and collections. So let's talk about properties of MongoDB. When you're inserting a document into MongoDB in a collection, the following things all happen. Well, one, the document gets inserted into a flat file. That's going to be where the document lives. You're going to have associated entries for the document going into secondary indexes and the ID index. So when you do a lookup by secondary index, these are the data structures that you look up to actually find your information. You're going to have an entry for the operation being written to the oplog collection. For those familiar with relational databases, this is conceptually the same as a binary log. It's what's recording the operations to be replayed on other members of your replica set. And lastly, you have data being written to the journal to reflect this change. So when you do something as simple as a single write, whether it be an insert, an update, or a delete, all of these things are happening together. And in fact, for this functionality, you, the MongoDB developer, you're going to require that the data in your flat files, your secondary indexes, your oplog, and your journal all be in sync. That means if you have an item, in the flat files that says this is a document, you need those associated entries in the secondary index so you can find the document when you're doing a lookup by a secondary index. You need that associated entry also in the oplog to make sure that it gets replicated to all your secondaries, or for those familiar with master-slave terminology, to all your slaves, such that replication works properly. Otherwise, so all is sort of, hopefully you see what I'm getting at when I was talking about a transaction being a bunch of sort of work being done together. For MongoDB, this is the list of work that you require to be done together.
Yeah, so it's not just that you're trying to make a lot of database operations at the same time. It's that even internally, there's a lot of work that needs to happen consistently, right?
Yeah. So the point, yeah, exactly. So in fact, with what MongoDB does for what a MongoDB transaction is, it's all the work that is required to give you the rich functionality of replication and secondary indexes, and also crash recovery. So, in fact, on this slide here, I've written the 4 operations that constitute a MongoDB transaction. Write the document to the flat file. Write the associated keys to the secondary index. Write the entry to the oplog. Write the entry to the journal. These units of work put together make up a MongoDB transaction. So sometimes when people ask, is MongoDB transactional, I like to answer with an emphatic yes. It is transactional. And these are the types of transactions that you get. So what I want to do now I want to actually get into the example that you were asking about, is try to understand how these 4 operations honor the ACID properties. And one key thing to understand is for this is MongoDB's locking. So I don't know if people are familiar with the fact that MongoDB up through 2.6 has a reader-writer lock for each database, which means inserts, updates, and deletes, use a write lock, whereas queries, such as finds and the aggregation framework and count and distinct, etc., they use a read lock. So, and this is going to be important as we try to understand how MongoDB honors the ACID properties, is that the key thing to remember is only one thread can make modifications to a database at a single time. So now let's talk about each of the four properties. Let's starting with MongoDB atomicity. Namely, either all these operations succeed or none of them succeed. And that's a good thing, You're never going to have a document's secondary index exist without the full document existing in the main data store. So this is something conceptually you hear about related to MongoDB, that they talk about MongoDB has quote-unquote single document atomicity. This is what it's referring to. Now let's talk about consistency, and the key thing with consistency is the execution of the reader-writer lock, where, remember when we talk about consistency, is that the database is always transitioning from one valid state to another. And sort of the way that we've defined what a valid state in MongoDB is, this is having the oplog, your secondary indexes, and your main data store being in sync. Right? So you're always transitioning from one of those valid states to the other. And the way MongoDB ensures consistency is with their reader-writer lock. No matter what your multiple threads are doing, the data in your collections is always going to be in sync because only one document is being changed at a given time. So hopefully that answered your question about consistency. Like, you want to transition the database. When you're doing an insertion, beforehand, the insertion doesn't exist. You grab the lock, you do all the modifications necessary, and afterwards, the insertion doesn't exist. The secondary indexes are updated, the main data file is updated, the oplog's updated.
So, for example, to maintain consistency in an update of multiple documents, what you mean by moving from one valid state to another is, for example, that it would have to modify each document individually, and then when one document is modified, then it's in a valid state, and then when the second document is modified, it's in a valid state, and so on and so forth.
So your question was about being able to consistently modify multiple documents, and so the key thing to understand is that the valid state transitions are one document at a time. So if you're modifying 5 documents, after you modify you transition from 0 modified to 1 modified to 2 modified to 3 to 4 to 5, and each of those is considered a consistent state. What is not consistent is if your modification, for example, makes your secondary index invalid, like the associated entries in the secondary index aren't properly updated. So we're jumping ahead a little bit, but sort of, just to sort of peek ahead, one thing that I'm sort of driving at is all the transactional semantics in MongoDB are centered around a single document. So let's quickly talk about isolation, because once again, the reader-writer lock is crucial for the isolation. And and to understand isolation is, when are documents becoming visible for queries? Well, queries are using a read lock, so as long as the query is handling only one document, the query is guaranteed to be holding a read lock, and it's guaranteed to be reading something that belongs in the database, because concurrently there are no writes that are occurring. So once again, the reader-writer lock is what is providing isolation. And for durability, MongoDB uses journaling, meaning write operations written to the journal before it's applied to collections, and on recovery, the journal is processed to restore the database. Now, I don't want to get into further details on this. The main point that I'm trying to make here is that what people are maybe familiar with logging and recovery in relational databases, MongoDB has journaling to provide that same functionality. So the MongoDB durability is there and it does exist. But the key takeaway that I want us to take from what I just presented is MongoDB is transactional when you're dealing with individual documents. And MongoDB is not transactional when you're trying to deal with multiple documents. So now I would like to transition into the multi-document behavior of MongoDB. So to discuss multi-document behavior, what I'm going to be doing is I'm going to be stepping through each of the type of operations, and we're going to see how MongoDB can behave when you're dealing with multiple documents at a time. So let's begin with insertions. Now, suppose I have a unique index on A, and I do the following insert of A1, A2, A3, A1. Now, the reason I'm doing this insert is what I'm doing is in one statement, I am inserting 4 documents, but you notice there's a uniqueness violation here. We said A has to be unique, but the very first element we're inserting and the last element we're inserting is going to be violating that constraint. So what happens when you run that statement against MongoDB is you're going to notice 3 of the insertions made it and the 4th one did not. And this is sort of the key thing this is one of the key things to understand when you're dealing with multiple documents in MongoDB. So if a batched insertion fails, the state of the database is technically unknown. Any number of the inserts may have succeeded. So in the previous example, our batched insert had 4 documents in there. It failed, but it happened that 3 of the 4 made it, but we don't know. It could have been 0, 1, or 2 of them. Now let's take a look at updates and deletes. Suppose you have a collection with the following documents, and the key to see with this is that for all these documents, the value for A is 10, and the value for B is different. It's 10, 100, or 1,000. And I do a simple update where A is 10, I want to increment B by 1. Well, what happens? By default, updates and delete affect only one document that matches the query. And the reason for this is, once again, they're taking advantage of MongoDB's single document transactional behavior. If multiple such documents exist, which document is going to change is actually unspecified. So for this statement that I just presented, you actually there could be 3 possible successful outcomes. You could have the first document updated, you could have the second document updated, or you could have the third document updated. It could really be either one. Now, if you want to try to update or delete all of the affected documents, you're going to have to pass in multi is true to your update statement. But if you pass multi-true, one thing you as the application developer need to be aware of is that on failure, just like inserts, the state of the database may be unknown. Were any documents updated? If so, how many? Which ones? And for this example that I was just showing earlier on, you could have, for this example, the successful outcome would be all 3 documents being updated. But on failure, you could have a number of different outcomes. You could have none of them updated. You could have these latter 2 updated. You could have just the first one updated, just the second one updated. You could have a variety of different outcomes that you as the application developer need to be aware of to handle. So now let's transition to what happens when you're dealing with queries. And the main point to remember about queries is that the read lock is held when you're retrieving an individual document, but the read lock may be yielded before getting another document. So one thing that can happen is multiple documents that are fetched may come from quote-unquote different points in time. And to give an example of sort of what this means and what can be happening is, suppose you had a collection foo with an index on A and the following documents, IDs and ID1, A11. Now, but in two different connections, I run the following essentially simultaneously. And what I'm trying to do here is I'm trying to set up essentially a race condition. I'm trying to set up a find in one thread, A greater than or equal to 10, and an update in another thread where we're incrementing A, such that the result of the update can collide with the result of the find. So and this will illuminate what can happen in MongoDB and sort of what you as a developer need to be aware of. So in a transactional system, or I shouldn't say a transactional system, that's not quite accurate. In a multi-document transactional system, the query returned is either going to be the state before the update, where A is 10 and 11, or the state after the update, where A is 12 and where the value of the update is 12. So you're either getting the pre-image of the update or the post-image of the update, because those are the valid states your database ought to be in. But with MongoDB, your query may actually return this. And you'll notice that first and third document of ID of 0 is being returned twice, with both the pre-image and the post-image. So how is it possible that this can be happening? Well, the order of operations can be, the thread doing the query can grab the read block. It can retrieve ID 0A10 for the query and say, all right, that result's going. Then the read lock can be released. The update thread can sneak in, grab the write lock, and do the update, and in doing so, update the secondary index. And then when the read lock comes to finish off the query, it's going to pick up the repositioned document of ID 0, where now it's 12. So in summary, when you're querying on multiple documents, sometimes you could have documents shift around on you, and you could get inconsistent and strange results. So in summary, once again, if your write operations span multiple documents and fail, the resulting changes may vary. And if your read operations span multiple documents, then the results may contain data from various points in time. So hopefully...
I think the problem there in the first point is not necessarily that the resulting changes may vary, it's that we don't have visibility of how they're varying, I guess.
Yeah, so we were saying how we don't have the ability to know how they're varying. I believe in MongoDB 2.6 they've done a lot of good work with their bulk commands to be able to give you data on sort of what's succeeding and what's failing. So I think actually MongoDB has made great strides to make that information more easily accessible. So there have definitely been great gains done between 2.4 and 2.6 in this area. So, but also another good thing, another point that I want to make is that, at the end of the day, you're still getting, with MongoDB's transactional semantics, secondary indexes and replication. Like, those are powerful features that users need. Like, secondary indexes are a very powerful feature to have, and it's through their transactional semantics that they're able to deliver this. So with that being said, hopefully now that we understand, how multi-document operations behave, let's take a look at sort of what can be done to deal with them in MongoDB. So at a high level, there are several approaches. One approach is sort of realize it doesn't matter for your application. Another is sort of the don't do it approach. It's kind of to say, hey, doctor, when I do this, it hurts. Well, don't do that. Hey, I have multi-document operations. They're not transactional. Well, don't have multi-document operations. Another is try to collapse a bunch of things into a single document. And lastly, you could try to develop application code as a workaround. So let's actually examine what each of these are. And the first one is the it doesn't matter, sort of the it doesn't matter. And a good example of this is time series data. Sometimes just given the characteristics of your application, you don't need to worry about concurrent writes and reads conflicting with each other because you, as the application developer, know that's not going to happen. So if you have time series data where all your data is being inserted with the current timestamp, you can safely do queries from, yesterday, last week, or last month because you know that data is not changing. All the new data is coming today. It's not coming from the past. So with such applications, they say, oh, well, what if your queries conflict with writes? You could just say, it doesn't matter, because for my application, I know it won't. The next one was sort of that I said is don't do it, and that's have all your operations, if you can, deal with a single document. Insert documents one at a time. Don't batch them up. Don't run updates and deletes with multi to be true, and try to make your queries operate on a single document. Now, the downside for this is you may be giving up significant performance gains because batching documents together reduces a whole bunch of network overhead. So an insertion experiment we did with MongoDB and TokuMX, we have a benchmark, IIBench. You can Google it, read about it. It shows why TokuMX's insertion performance, write performance is so wonderful. But the really important thing we did was, we did a simple test where we insert one document per statement into MongoDB and TokuMX versus 100 documents per statement in MongoDB and TokuMX. And you notice in both cases the performance was better when you were batching the insertions to 100 per statement. In TokuMX's case, it was much better. So yes, you can deal with documents one at a time, but one thing you got to be aware of is that you're going to be possibly losing performance that you get with batching.
But what if you still insert, like you have a separate thread or process inserting even one at a time? Couldn't that read log and write log yielding still happen?
So the question, if I heard correctly, was if you're doing the insertions one at a time, can you have that read and write lock yielding still happen?
Yeah,
so the read
is being done by another thread or process.
So the read and write lock yielding in I should say 2.4 and I believe 2.6, it's only done when the subsystem thinks is going to be doing an I/O. So the yielding does, as far as I know, doesn't really impact performance that bad. Like you don't lose performance from yielding. So
no, I'm referring to the consistency part, right? Not the insert performance.
Yeah. Well, MongoDB, the lock is definitely yielded in between insertions. So MongoDB is not necessarily going to be, is not transactional, between insertions. So basically one thing you need to do as an application developer is you just need to think everything is changing one document at a time. Your state transitions for your database is happening one document at a time, and it's just something you got to understand as an application developer.
Right, but what I am really getting at is that, for example, in that find, where we got multiple, like we got the duplicates of the same document in different points in time. Like even if you insert one at a time, that could still happen, right? Your find could still be interrupted, like your cursor.
I see. Yeah. So the question was, even if I insert documents one at a time, the example that I showed with queries returning the same document multiple times can still happen, and the answer is yes. And sort of to deal with that, we get to the next thing that I was talking about is collapsing documents, if you can, to basically also have your queries dealing with one document at a time. Try, instead of inserting multiple documents, try to find a way to inject one document containing all your information such that your queries will also be retrieving one document with all of this information. And you see, a nice thing that you could do here with MongoDB that is a lot more challenging to do in relational databases, you can take advantage of the richness of document databases, the richness of what each document can look like. You know, take advantage of the fact that you can use arrays within a single document. So for what you were talking about, this is one thing you want to look into. And lastly, sort of the quote-unquote just deal with it is MongoDB. There are some good cookbooks, so to speak. Well, I shouldn't say cookbooks because that's in the URL. There's some good pointers online where if you need to develop application code around the fact that there are multi-document transactions, there are resources online that you can use to essentially develop application code around that fact to hopefully get you to what you need to do. So if what I've said up till now isn't good enough, I recommend you reading these links. So with that, I've hopefully covered what MongoDB's transactional semantics are. And now what I would like to do is so now that we understand how MongoDB behaves, sort of, what the benefits are, and there are some very good benefits, but also what its drawbacks are, I would like to present what TokuMX, the product that I work on, I'm a developer at Tokutek, what TokuMX does to address these things. So let's actually discuss just quickly what TokuMX is. TokuMX can be thought of as MongoDB with improved storage. And it's completely open source. What we've done at Tokutek is we took MongoDB, we completely ripped out all of its storage code, and we've replaced it with our own storage code that's built on top of our own storage engine, which is built on top of fractal trees. It is a write-optimized engine. And so the keys, as an application developer, what you need to know is it is close to a drop-in replacement for MongoDB version 2.4, meaning replication sharding just works. The query language, the same. The data model, the same. Your drivers should just work. From a compatibility standpoint, just the thing, I don't have it written here, I'll mention. Currently, with our latest release 1.5.1, we don't have geospatial indexes or full text indexes. In our upcoming release 2.0, which will be released very soon, we will have geospatial indexes. But the main thing to know is that really, hopefully, you could just take TokuMX, download it, drop it in, and with few to no changes, have it just work. And the reason we did TokuMX is because our storage core that the core that we ripped out from Mongo, that we replaced with, has a bunch of benefits. And the top benefits are compression. In fact, this is the benefit that you will always get. Like, I have never heard anyone say that we don't compress. Like, you get up to 25x compression. And for those wondering, well, gee, up to 25x, how do I know if I'm going to get the 25x? It all depends on how compressible your data is. If you're storing JPEGs in your documents, it's not going to compress that well. If you're storing URLs, it's going to compress wonderfully. You get improved write performance on large data. You get improved sharding, faster queries, much faster migrations, lower overhead migrations, so you don't necessarily need to schedule migration windows. And you also get sort of these last two items that I put in bold print, scale up and multi-statement transactions on non-sharded clusters. Now, with scale up, concurrency is a performance benefit. Multi-statement transactions is an application benefit. And the reason I put these in bold is because these are direct consequences of us putting in a multi-document transactional storage into MongoDB to create TokuMX. So what I'd like to do now is I want to present what TokuMX's transactional semantics are. And hopefully it's going to be simpler to explain than MongoDB. So what TokuMX provides is multi-statement and multi-document ACID transactions, queries that use multi-version concurrency control, MVCC, which means they operate on a snapshot that does not change for the duration of your query, and we have document level locking available to increase the concurrency instead of database level locking. So I want to take a step. I want to take a moment here to just discuss performance a little bit. So as I mentioned earlier, MongoDB uses a database level reader-writer lock to provide transactional semantics. And like one of the key things that I feel like isn't talked about a lot, when we're talking about current MongoDB, is that one of the benefits, one of the reasons you have the reader-writer lock is to provide these transactional semantics. So TokuMX, on the other hand, has document level locking, and as a result, that improves your concurrency. So TokuMX's multi-statement transactions and its concurrency, they're sort of attached to the hip together. They go together and you get the benefits together. And this is what leads to, at times, significantly better performance on mixed read and write workloads. So and here is a graph of a benchmark that we've run in-house. Sysbench is a well-known MySQL benchmark that we ported over to MongoDB, and we ran an in-memory benchmark for TokuMX and MongoDB, comparing actually an older version of TokuMX 1.2 with MongoDB 2.4.6. And you'll notice TokuMX is scaling because we have document level locking, and MongoDB is not scaling so much because they have database level locking. Now, one of the keys here is to realize is this is an in-memory benchmark, so IOs aren't an issue here. Now let's talk about what the behavioral semantics are with respect to inserts, updates, and deletes. And with TokuMX, it actually is quite a bit simpler. Each statement that modifies a collection is either fully applied or it's not applied at all. There's no in between. You don't have to worry about whether a subset of my change is made it or not. This means you can safely batch your documents for insert because an error is not going to leave the database in an inconsistent state, and you can safely set multi to be true for your updates and deletes. On any error, you're assured that the database's state is going to be unchanged. So, as an example of TokuMX's transactional semantic, let's sort of bring back the example that I gave earlier. We create a collection foo. We then ensure an index such that the index has got to be unique. And if I do an insertion where the uniqueness is violated with A1 here and A1 here, I get my error of a duplicate key error, but then I go to find the documents and I'll see no documents are returned. So unlike MongoDB, the statement is never partially applied. Now what I'd like to do now is let's take a look at queries. So queries use MVCC and thereby use a true snapshot of the system. So looking at the previous example where I have these two documents and I'm going to do essentially conflicting operations at the same time, where I do a find and an update concurrently, where the update is going to impact the results of the find. With TokuMX, you're going to get a good answer all the time. You're either going to return the pre-image of the update or the post-image. So you're going to get a more consistent result. In fact, within TokuMX, we've added the following commands for multi-statement transactions. I'm just presenting the shell wrappers here. These are wrappers for actual commands where you can run begin transaction, and then you can either commit or roll back the transaction. Whoops, I went the wrong way. And just an example of multi-statement transactions, I tried to color code this slide to make it a little simpler, where in black you have we first do the insertion. We do a find to see that the insertion made it. Then I begin a transaction, and I do an insertion with the ID during transaction. And while the transaction is still running, I do another find. I'll see both documents, both the before and the during. But now if I roll back the transaction and I do another find, you'll see that the ID that we inserted and found previously is no longer there. And for those of you that are familiar with relational databases, hopefully this is all familiar as well. These are the same common begin, commit, and rollback that you find in relational databases. And the MVCC query semantics also extend to multi-statement transactions. So suppose, once again, I have a collection that has a single element that was inserted before snapshot. Now, in one thread, I begin a transaction, so that creates my snapshot. Now, later, in another connection, I do an insertion, and this insertion committed. And then I do a find, and I see that this insertion is there. So the key to understand about this insertion that I have in connection 2 is this insertion is there. Like, the machine can go down and come back up, and that document is still going to be there. But in that first connection where I have a transaction open, if I go to perform the same query, I'm still not going to see that document because that document was not there when I created the transaction. So you're going to note that the query results aren't going to contain the insertion made. So hopefully by now what I've done is I presented TokuMX's transactional semantics, and hopefully as a developer you will see some of the benefits provided with this extended functionality. But one thing you also need to be aware of is some gotchas. And these gotchas are a result of you, the developer, taking advantage of more powerful semantics. Sort of, you've got these more powerful semantics. You got to be careful how you use them, otherwise they could have some bad consequences. And these are issues that also exist in MySQL as well and other relational databases. So really this section, these gotchas are for those that may not be that familiar with some transactional relational databases. So let's take a look at the first example here. In connection 1, I begin a transaction, and then I go and I update a document, but I never commit it. In fact, I update it, and then the developer goes to lunch. He goes on a nice extended lunch, talks to his friends, etc. Never gets around to committing the transaction. Another thread comes along and tries to update the same document. What's going to happen? Well, there's going to be a timeout because connection 2 can't proceed with that update until connection 1, either commits or rolls back its transaction. And because it hasn't, connection 2 has no recourse but to timeout. Now, let's take a look at another gotcha where suppose you do the following sequence but with no indexes. And the key thing that I want to point out here is you have no secondary indexes. In one connection, I begin a transaction and I update a document where B is 1. And I don't commit it, I go to lunch. Now in connection 2, I do an update where B is 2. So a completely different document. But what happens with connection 2 here? What ends up happening is you're going to have contention. And the reason for that is even though both threads are writing different documents, they each need to do a collection scan to find which documents to update. And these collection scans are going to take locks. So the contention isn't coming from connection 1 updating B1 and connection 2 updating B2. The contention is coming from both connections having to do a full scan in order to find the documents it needs. And so really the moral of this specific example is make sure your updates are properly indexed. Otherwise, you're going to really hurt the performance of your application, even more so with TokuMX, because the locking that's going to be taken is going to be much worse. So be careful. But also, sort of the other thing is when you're doing updates and deletes, don't just think about what you're writing. Think about what you're going to be reading to do those updates. So, and the next gotcha I would like to discuss is the following. Now, in this sequence, I have two connections, 1 and 2. Each of them are updating the same documents. One of them is updating 0, the other's updating 1. And let's assume they're both responsible in that they're going to commit the transaction as soon as they're done. Sort of in my previous example, I'm saying the developer is going off to lunch, and I'm using that as a way to say, let's suppose the transaction takes a very long time. In this example, the developer is not going to lunch. In fact, the developer is going to try to commit the transaction as soon as these are done. But what's happening here is, because they're updating the documents in different orders, you're going to end up getting, you run the possibility of getting a deadlock. So connection 1 is going to successfully update 0. Connection 2 is going to successfully update 1. And now, as these connections try to proceed, they're going to be trying to grab a lock on, they're going to require a lock that the other connection has. Connection 2 needs a lock on 0. Well, connection 1 has it, and it hasn't given it up yet. Connection 1 needs a lock on 1. Well, connection 0 has it, and it hasn't given it up yet. So this is a classic example of a deadlock that is possible to get in TokuMX, but you wouldn't, or any database that gives you multi-statement or multi-document transactions that isn't currently you can get with MongoDB. So this is something you also need to be aware of. So the moral of the story here is, with TokuMX's transactions, is TokuMX's transactions and its document level locking are very powerful. You get essentially more tools available at your disposal as an application developer. You get what I like to think are stronger semantics on your statements. But one thing the user needs to be aware of is they need to be aware of the implications that they have on their application. So with that being said, that concludes the presentation. I'll open it up for if there are any questions.
I don't have any questions. No, I think thank you so much, Zardosht. That was really interesting. I was wondering why the default for updates was just a single document. That always got me, because in other database technology, the default is the opposite.
Yeah, so I gotta say, I think I can't say why the reason is that the default for MongoDB's updates are multi to be false, but it makes sense to me.
Yeah, I mean, it makes sense that it's because of the transactional.
Yeah.
It's much more advantageous to do uprights in like in a transactional way. So that makes sense for that to be.
Yeah, and one thing it does is it drives the application developer to be thinking in terms of single document atomicity, which sort of helps protect the developer from making a mistake in their process.
Yeah, it's subtle, but yeah, it does help.
Yeah. So, all right. Well, thank you very much. Thanks a lot for the opportunity for having me speak. Thanks for attending. And
it's our pleasure. Is there any last words of wisdom or any message that you want to leave us with before you go?
Well, I think I guess the last words of wisdom that I could say is, MongoDB does a wonderful job of, making the database simple to use, really simplifying things like replication and sharding. But databases, by their nature, are just one of those aspects in development where you need to understand what's going on. You really need to have an understanding of, you need to have some basic clue of what's happening underneath the covers. Otherwise you will get bitten. So I guess the last words of wisdom is try to understand what your application is doing and why.
Right, that's great. That's great. Thank you,
All
Zard.
right.
It's a pleasure to meet you and to hear you speak. And
Uh,
thanks for coming.
all right. Thank you very much. Have a good night.
Good night.
Bye.
All right, guys. I think that's a wrap for us. Thank you for watching, and I hope you found it useful. Good night.